Good morning. Today we will learn another example for minimum state automated. So this is another example. So consider the minimum state automated, which is equivalent to the transition diagram. This is the transition diagram. Carefully note this diagram. In this diagram, we observe there are 7 states, one initial state that is Q0, and one final state that is Q3. And the inputs are A and B. So the given final automated set of states, set of inputs, function, transition function, initial state, final state. So the set of states Q0 to Q7 and the inputs A to B. And the transition table can be represented by. So this is the transition table. So carefully note this table by using the above diagram. Okay. So now we construct a minimum state automated. So now we construct minimum state automated. It is represented by M dash, which is equals to Q dash sigma delta dash Q naught dash and capital F dash, which is equivalent to the given finite automated. So for this, we have construct equivalent classes, that is denoted by pi. So equivalent class elements are classes. Classes are class elements. So that is the first we construct for this. First we construct 0 equivalent class elements. 0 equivalent class elements. So for this, first we consider the set of final states and set of non-final states. So in this diagram, only one final state, that is Q. So it can be treated as one element. So therefore the first element. Therefore the first element in I0 equivalent, sorry, we construct I0, okay. I0 equivalent class. Class is denoted by Q1 naught. That is, what is the final state here? Q. So that is Q. And the remaining elements are Q1, Q0, Q1, Q2, and Q4, Q5, Q6. This can be treated as second element. So the next element. The next element in 0 equivalent class is, it is denoted by Q2 naught. Rest of the elements are Q0, Q1, Q2, Q4, Q5, Q6, and Q7. So now we can start. Now we have to construct one equivalent class elements. One equivalent class elements. So one equivalent class elements. So that is I1, it is denoted by Q11, Q21, Q31, and so on. So here, what is the first element in I0? Q. So here only the singleton, so it cannot be partition further. So it has the element. So let's consider the set F. Consider the set F Q1 naught, that is single and Q which cannot be ascend further. So we take it as the first element, take it has first element in pivot. So that is therefore Q11 is the embed single and Q. So now consider the second element in pi naught. So consider the set Q2 naught, which is equals to Q naught Q1, so Q1, Q2, Q4, Q5, Q6 and Q7. So now we consider one equivalent field. So we check it. One equivalent of Q0 and Q1. So that implies del R of Q0 at the input Y. Similarly, for Q1 at the input Y and Q0 at input B, Q1 at input B. So by observing that lattice is able. When input Y is applied to the state Q0 in motion of Q1, similarly, and Y is applied to the state Q1 in motion of Q0, and likewise. So that implies Q1 and Q0. Similarly, when B is applied to the state Q0 in motion of Q0, and B in motion of Q2. So when Q1 belongs to Q2 naught, Q1 belongs to Q2 naught, and Q0 also belongs to Q2 naught. So that input Y both the states belongs to the same set. For input B, so Q0 which belongs to Q2 naught, and Q2 which belongs to Q2 naught. So for B also both the states belongs to the same set. So therefore Q0 and Q1 are one equivalent. Are one equivalent. One equivalent. So now for Q0, Q2, thereafter Q0, Q4, thereafter Q0, Q4, and likewise. So now check it. One equivalence for of Q0 and Q. So that implies del R of Q0 at input Y, del R of Q2 at input Y, and Q0 at input B, and Q2 at input B. So by observing the lattice is able, we note that at input Y Q0 motion to Q1, at input Y Q2 motion to Q3, and at input B Q0 motion to Q0, and input B Q2 motion to Q1. So clearly here Q1 belongs to Q2 naught. Q1 belongs to Q2 naught. But Q3 belongs to Q1 naught. Q3 belongs to Q1 naught. Here Q2 naught and Q1 naught. Q0. So at input B, both the states belongs to the same set. But at input A, Q0 belongs to Q2 Q2 belongs to Q1. So here's the difference. So therefore, Q0 and Q2 are not one equivalent, or not one equivalent. So now consider one equivalence of Q0 and Q4. Q0 and Q4. So by observing the transition table, we conclude that by observing the transition table, we conclude that Q0 and Q4 are not one equivalent. So that is by doing the same process for Q0 and Q4 like this, we find that Q0 and Q4 are not one equivalent. So check yourself, and similarly now consider the one equivalence of Q0 and Q5. So same by observing the transition table here also. By observing the transition table, Q0 and Q5 are not one equivalent. So one equivalent. So similarly, Q6. So again, by observing the same table, we get Q0 and Q6 are not one equivalent. Finally, one equivalent. So therefore, we take it a new set that is Q2 dash has the states which are the equivalent to each other. So those elements are Q0, 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 Q1. So Q0, Q1, and Q2. Q2 is not one equivalent. Q0, Q4 are not one equivalent. So Q0, Q5 are one equivalent, so for Q5. And Q0, Q6 are one equivalent, so that implies Q6. So the remaining elements in Q2 naught are. What is the elements in Q2 naught? Q0, Q1, Q2, Q4, Q5, Q6, Q7. So out of these Q0, Q1, Q5, Q6. So Q0, Q1, Q5, Q6. These are all one equivalent to each other. The remaining elements are Q2, Q4, Q7. So the remaining elements are Q2, Q4, Q7. So now check it. One equivalence of Q2 and Q4. So by observing the transition table, we observe that these are one equivalent. So therefore Q2 and Q4 are one equivalent. And check one equivalence of Q2 and Q7. By observing the transition table, we conclude that Q2 and Q7 are not one equivalent. So check yourself for these two things. So therefore, here we take these two states as in one element and Q7 has in another element. So therefore, the last element in I1 is Q1, looking at set of Q1, Q4, Q2 and Q4, and the new element in I1 is Q4, one which is Q7. So therefore, I1 is Q1 dash, Q2 dash, Q3 dash, Q4 dash, where Q1 dash is, what is Q1 dash? Singleton. So what is Q1 dash? Then Q1 dash is Q3, where Q2 dash is, set Q0, Q1, Q5, Q6, and Q3 dash is Q2, Q4, and Q4 dash is Q7. So since I0 not equals to I1, so what I1 contains 4 elements where I0 contains 2 elements only. So I0 contains Q1 not, Q2 not. So I0 not equals to I1. So we construct two equivalent classes or class elements. That is I2 is equals to Q12, Q22, Q32, and so on. The first element in the I1 is singleton Q3, so which cannot be partitioned into further, so we take it as the first element. So since singleton Q3 cannot be partitioned into further, so we take it as the first element in I2, that is Q12, that is singleton Q3. So what is the next element in I1? That is Q2 dash. So consider the set Q2 dash, that is Q0, Q1, Q5, and Q6. So check the two equivalents. Check two equivalents for Q0 and Q1. So check two equivalents of Q0 and Q1. So that implies that of Q0, yeah. That of Q1 at yeah. That of Q0 at B. That of Q1 at B. that implies Q1 and it moves to Q0, it moves to Q0 and it moves to Q0. So by observing that lattice is able, we note this. So here Q1. So Q1 belongs to Q2 dash. So Q1 belongs to Q2 dash. And Q0 belongs to Q2 dash. Q1. Sorry. And similarly Q0 belongs to Q1. But Q2 belongs to Q3 1. Q2 belongs to Q3 1. So your input B. Does X, Q0 and Q1 does not belong to the same set. So therefore Q0 and Q1 are not equivalent. So let B, Q1, Q0 does not belong to the same set. So therefore Q0 and Q1 are not equivalent. So thereafter check the equivalence between Q0 and Q5. So check equivalence of Q0 and Q5. By observing that relaxation able, we conclude that Q0 and Q5 are not equivalent. Check yourself for this, and similarly for Q0 and Q6. So check equivalence of Q0 and Q6 is we conclude that Q0 and Q6 are equivalent. So therefore the next element is, what is the next element in I2? Q2. So the next element in I2 is nothing but these two states, Q0, Q6, which are the equivalent to each other. So the remaining elements is Q1 and Q5. Now check the equivalence for Q1 and Q5. So now check equivalence of Q1 and Q5. So we conclude that we are equivalent to each other. So therefore take these two elements as one set. That implies, the next element is Q1 3. So Q3 2. Q3 2. So that implies Q1 and Q5. And the next element is Q3 dash. So consider this set. Consider the set Q3 dash. That implies Q2, Q4. From which state? I1. From I1. So now check it. Equivalence of Q2 and Q4. Q2 and Q4. So by observing that lattice is able, we conclude that Q2 and Q4 are equivalent to each other. So therefore, it has the next element that implies Q4U, that is Q2, Q4. And the last element in Pi1. What is the last element in Pi1 is Q4, 1. That is single and Q7, which cannot be partitioned into further. So, therefore, take it the finally. So, therefore, the final element in Pi2 is Q5U, that is single and Q7. So, hence, the two equivalent class, which is the sets Q1U, Q2U, Q3U, Q4U, and Q5U, where Q1U is, where Q1U, what is Q1U? Q3. What is Q2U? That is single Q0, Q6. What is Q3U? Q1, Q5. And what is Q4U? That implies Q2, Q4. And finally, Q5U is Q7. So since I1 not equals to I1 not equals to I. Since because I1 contains 4 elements where I2 contains 5 elements. So we construct pre-equivalence class elements, that is denoted by I3, and the section is Q13, Q23, Q33, and so on. So on. So, consider the first element in Pi2, that is Q1, that is Q3, which cannot be partitioned into further. So we take it as the first element in Pi3, that is Q1, Q3. And the second element in Pi2 is Q0, Q6. By observing that transition table, clearly Q0, Q6 are pre-equivalent. So take it as the last element in Pi3. So that is Q0, Q6. So similarly, Q1, Q5, those are pre-equivalent, so take it as last element, and Q2, Q4 are pre-equivalent to each other, so take it as a last element, and similarly, Q5 is Q7, so therefore I3 is Q1, 3, Q2, 3, Q3, 3, Q4, 3, and Q5. Since I2 is equals to I3. Since I2 contains 5 elements, I3 contains 5 elements, so we stop the process here. So therefore, take it has the equivalent, that is, what is Q13? What is Q13? Single and 3. So that implies Q3. What is Q23? Q23 has Q0, Q6, so it can be denoted by Q0, Q6. And what is the Q33? That is Q1, Q5, so it can be denoted by square brackets Q1, Q5. So make it, so here we make it as a square brackets. So what is Q43? That is Q2, Q4. So that is Q2, Q4. What is Q53? Q7. So here the initial state is, so this is the initial state, because by starting, what is the initial state here? Q naught. So Q naught ಮುಂದೆ ಒಂದು ಇದಕ್ಕೆ ಒಂದು ನಾವು this is the initial state, and Q3 is the final state. So now this is the final state. This is the final state. So the construction of a minimum finite state automaton. So minimum finite state automaton. So carefully note this table. So here Q0, Q6 is the initial state, Q3 is the final state. So when A is applied to the state Q0, it moves to Q1. And A is applied to the state Q6, it moves to Q5. So therefore Q1, Q5, and Q0, Q6. But here we observe that when Q7, only at Q7, when A is applied to the state Q7, it moves to only Q6. But here we write this Q0, Q6. ఎందుకు రాసేమలాగా ఇక్కడ చూడండి ఈ టేబుల్లో Q6 సపరేట్గా లేదు, దేనికి కంబైన్ అయి ఉంది? Q0, Q6 ఉంది. అందుకని ఈ స్టేటే మనం ఇక్కడ రాయాలి. కానీ ఇనీషియల్గా Q6 ఉన్న దీని ప్రకారం సో ఈ ఎలిమెంటే మనం రాయాలి. అందుకని ఇక్కడ ఏమవుతుంది? Q0, Q6. బట్ అదే బి వెళ్ళింది అనుకోండి, మన ఇన్పుట్ బికి Q7 అయితే Q3, దాన్ని సింగిల్గా రాయొచ్చు. ఎందుకు? Q3కి సింగిల్ ఉంది కాబట్టి Q3గా రాయొచ్చు. సో carefully note the point and the respect to transition graph. Okay. Thank you.